We're going to go over some examples for to conclude our chapter 2. So one of the discussions was to relate electrons to charge. So right here we are going to go over example 2.1, and the question is how many coulombs of charge do 93.8 times 10 to the 16 electrons represent? So we are going to use this formula that says charge is equivalent to the number of electrons divided by 6.25 times 10 to the 18 electron charge. So we just write down the number of electrons that are given us and we copy the same number. Where do we get this number from? If we go back to our PowerPoint presentations, we saw that the charge was defined as 1 electron over the charge of an electron. So that's how we get this number over here. If we divide it, we get 15 times 10 to the negative 2 coulombs, or we can write it in engineering prefixes as 150 millicoulombs. We continue in example. We continue with example number 2.2. We have 50 joules of energy are required to move 10 coulombs of charge. What is the voltage? So from the voltage definition, we know the voltage is equivalent to the work required to move the charge against the electric field. So we just plug in, we have 50 joules over 10, we get 5 volts. Just a plug in. Problem number 2.3. We have 10 coulombs of charge that flow through a given point in a wire for 2 seconds. What is the current? Again, we just use the definition of current, and it says that the charge is a rate. So a rate is defined by time. So the charge divided by the time, 10 coulombs divided by 2, we get 5 amps. When we do circuit analysis, we use conventional current flow. That means we go from positive to negative. We go clockwise. So this is the direction we are going to use when we analyze our circuit. So we go from the positive terminal of the voltage source, following the path, we go through the resistor, and then we get to the negative part of the terminal. We agree it was going to be the negative of the ground. How to measure voltage? So we have our circuit, a basic circuit. We have voltage source and we have our resistor. We can only take measurements across electronic elements. We cannot measure between this point and that point because we discussed and we agreed that this point and that point would be the same. So if we measure the voltage across that point, the answer is going to be 0. Ideally, we said that we have no losses when we connect components using wires. So we continue with that convention. So right here we can only measure voltage across a electronic component because we want to measure how much voltage is consumed by that component. So it has to be a component. It cannot be just a wire. So right here we're going to measure the voltage across, or the voltage drop across this resistor. So we put our DMM into the voltage reading setting. Then we put the positive lead or the red lead first, closest to the positive, and we put the negative or the common on the other side. Doesn't matter how you do it. If we follow this convention, we are going to get a positive reading. If we flip, if we put the black over here and the red over here, we get the same numerical value but with a negative sign in front of it. What that negative means, it is that we have reversed the polarity of the current. So the DMM knows and follows the conventional path for current, positive to negative. So if we put the positive on this end and the negative on that end, it's going to tell us we assume the wrong direction for the current. The same way we measure resistance, it's just across. We don't have to do anything to the circuit. We just change the setting to read resistors now, or resistance, and we leave the same connections. We don't move the leads either. We can use the same lead connections. When we measure current, that's a different issue. We have a regular circuit, but now we are measuring current. So we know the convenient or the standard direction of current. So in order to measure current, we have to make a voltmeter part of the circuit. We have to open. Now current comes this way. It is forced to go through the multimeter, across, down, and continue to the resistor. Very important. We also have to change the lead to where it says that it is for current, and we have to put it in the current settings. Let's continue with another example. This is a problem. It says a resistor with a current of 5 amps goes through an amplifier circuit that converts 2000 joules of electrical energy to heat. It can be a heater in 35 seconds. What is the voltage? So let's write down what we have given. We have work, 2000 joules. How do I know it's work? Because of the units. Time, they're telling us that it's 35 seconds. Since it's in seconds, I don't have to do any conversion. And then current is giving us 5 amps. They want to know the voltage. I write my definitions. Voltage is equivalent to work over charge. Current is charge over time. So I want voltage, but I don't have charge. So I use this other formula to find the charge. So over here I solve for the charge. So Q becomes current times time. So I use plug in, I find my charge, and then I use the second definition where I have the work over the charge and I find my voltage. So right here is a two-step. First I have to solve for the charge, and then I have to use the charge to find my voltage. Now we are going to go and study resistors. Remember the color code table that we talked about? So we are going to use that table to help us solve these resistors. I didn't draw them because I didn't have enough colors for the color band, so I just showed the values, the color that the band would be. So I have red, black, brown, silver. So red is 2, black is 0, brown is 1. Is the third band, so it's just a multiplier. And then silver is the tolerance, 10% tolerance. So I copy the first digit, I just copy down. The second digit, I just copy down. And then I have the multiplier. 10 to the power of 1 is just 10, so it's 20 times 10 ohms plus minus 10%, or it's just 200 ohms plus minus 10%. Another example, we have black, brown, orange, gold. So black is 0, brown is 1, orange is 3, and gold is 5. So I have 1, 0, any number has a 0 before it, so it doesn't matter. The orange, it is the multiplier 10 to the power of ohms plus minus 5% tolerance, which is gold, which is equivalent to say 1 kilo ohm plus minus 5%. Another one, we have green, brown, black, gold. Green is 5, brown is 1, black is 0, so I don't write anything. And then gold is just 5%, so it's 51 ohms plus minus 5%. Now we are going to go the other way around. Now we are going to go from numerical values into colors, which during the lab is how you guys would do it. I will give you a value and you will have to go into your toolbox for the color equivalent to that value. So it's important that we know how to read resistors both ways, in both directions. So 5 is green, 1 is brown, and then I have 1, 2 zeros, which are equivalent to red, and then the tolerance is a silver. then we have 20,000 ohm plus minus 5%. Right here, the first digit is a red because of 2. The second digit is a 0, which is a black. And then I have 1, 2, 3 zeros, which is equivalent to 3. So that would be orange. 5% is just gold. Okay. That completes our chapter 2 review. So now we are ready for our homework and assessment and quiz.